Alright, welcome to this edition of let's try to understand. Let's watch videos and try to understand physics. So this one's going to have some lightning and breakdown voltage, which is kind of interesting because it's kind of like the voltage that can slowly drain voltage. So it's useful for that, mostly. Alright, so let's let's begin. Now.
I mentioned to you that charge resides at the surface of solid conductors, but that is not uniformly distributed. Perhaps you remember that, unless it happens to be a sphere. And I want to pursue that today. If I had
yes, but well, generally speaking, everybody does put charge on spheres, so it's not that it happens to be on a sphere. So that's sort of the catch to all of this is when charge is relevant is usually in that circumstance. Sorry, I'm still having trouble with this monitor.
solid conductor, which say had this shape, then I'm going to convince you today that right here, the surface charge density will be higher than there, because the curvature is stronger than it is here. And the way I want to...
So that's the whole argument is right there. So, I mean, that's all you have to say to convince somebody, I think, is just to point out that the charges are really repulsive to each other, and that it just makes sense that the more curve there is, there's more distance per unit or whatever, and that they're likely to find it more pleasant to be on a higher slope, a tighter curve. I suppose there's a point where that becomes moot in the sense that they become you get too thin, then you have a problem.
Approach that is as follows. Suppose I have here a solid conductor A, which has radius r of A, and very, very far away, maybe tens of meters away, I have a solid conductor B, with radius r of B, and they are connected through a conducting wire. That's essential. If they are connected through a conducting wire, then it's equipotential. They all have the same potential.
Alright, which means the charge attempts to distribute itself equally on both surfaces. So clearly the big surface is going to have more of the little thingies, but the smaller surface is going to have ones that are closer together. No. Well, let's find out. Yeah.
I'm going to charge them up until I get a charge on QA here, and I get QB there. The potential of A...
Alright, the voltage. So the voltage is again, it kind of goes back to this argument that it has to be signified by something. Ionization, some sort of thing that changes the pressure of the atom, essentially. And there has to be, that's the only way you can contain or hold the pressure of the individual electron, is to have it connected to something else that gives it its identity, its pressure, its velocity. Quote.
is about the same that it would be if B were not there. Because B is so far away that if I come with some charge from infinity in my pocket, that the work that I have to do to reach A per unit charge is independent of whether B is there or not, because B is far away, tens of meters, and you can make it a mile if you want to. And so the potential of A is then the charge on A divided by 4 pi epsilon 0, the radius of A. But since this is an equipotential, because it's all conducting, this must be also the potential of the sphere B, and that is the charge on B divided by 4 pi epsilon 0 r of B. And so you see immediately that the charge...
The voltage has to be different on the two because the radius is different. So the radius is defining how ionized the atoms can be on the surface. I guess that's the way I would say it. How imbalanced they are. How you could have to be short 2 electrons, maybe. Something like that.
On B divided by the radius of B is the charge on A divided by the radius on A. And if the radius of B were, for instance, 5 times larger than the radius of A, there would be 5 times more charge on B than there would be on A. But
okay, there's more charge. That means there's more electrons that are ions, positive ions, let's say. So there's more of them, but they're in a position where they're further apart, so they look weak, where the other ones are closer together, so they look strong. Pretty much the definition, I think. So there's a better way of describing that idea, that the small radius isn't so much about creating more distance. It's about this, how much they diverge means they can be closer together. But I don't know exactly why that would be.
if B has a 5 times larger radius,
it might have to do with the fact that, say if they're sitting on a flat surface, they're going to feel each other's influence a lot more, right? So if they're radiating force at each other, you got these things sitting on the surface. If they're on a flat surface, their radiation is going to hit each other really easy. And the more bent the surface is, the more their radiation isn't going to hit each other. So they almost become invisible to each other. So even though they're closer together, they're invisible to each other. That's it. Okay, so the flatter you make the surface, so it's just about how flat the surface is. So don't think about, I mean, I know radiuses have to do with flat, but we usually don't think of it in those terms. But it's really how much off flat it is. So flat means they're going to feel each other's force the most, and they're going to have the most trouble getting closer together. And the more you unflatten the surface, the closer you can put them together, because their forces aren't going to hit each other. That is a good answer, I think.
then its surface area is 25 times larger. And since surface charge density, sigma, is the charge on a sphere divided by the surface area of the sphere.
So let's understand. Voltage is how close they are. That'll tell you how much voltage it is. How much amperage you got is going to be about, or current you can produce, is going to be about how much surface you have. And yeah, so you have more current or capacity on the big thing, but it's at a lower voltage because the little bits have to be further apart. These little bits have a certain amount of pressure, consistent on both. So both of them have the same pressure. That is, the little bits push the same amount. It's just that they can push against each other from a closer position on the little sphere than they can on the big one. So they're further apart on the big one. It's that simple. That's the simple answer. Less dense, even though there's more of them.
It is now clear that if the radius of B is 5 times larger than A, it's true that the charge on B is 5 times the charge on A, but the surface charge density on B is now only 1/5 of the surface charge density of A, because its area is 25 times larger, and so you have the highest surface charge density at A than you have at B. 5 times higher surface charge density here than there. And I hope that convinces you that...
So that the voltage is going to be much higher. So the density is really just saying how much is the voltage. So the voltage is going to be much higher on the little thing than on the big thing.
If we have a solid conductor like this, even though it's not ideal as we have here with these two spheres far apart, that the surface charge density here will be larger than there, because it has a smaller radius. It's basically the same idea.
He does throw in a new word now and then to edit his video, although he pops in a new, smaller radius. he edits himself a little bit, which is cool, to a point. You should sort of be stuck with what you do, but I understand fixing errors is good. I mean, I hate the idea that I have videos where I'm saying something and it's just, ooh, that was way wrong. So there are videos I'm saying something that's just way wrong. You just have to recognize that the new videos will attempt to correct that. Gratuitous girl picture.
So you expect the highest surface charge density where the curvature is the highest, smallest radius, and that means that also the electric field will be stronger there. That follows immediately from Gauss's law. If this is the surface of a conductor, any conductor, a solid conductor, where the E field is zero inside of the conductor.
So again, I would argue Gauss's law isn't a law that causes, it's a law describing effects. So the law is a consequence of the effects existing. The law isn't a description of the cause for the effect existing.
And there is surface charge here. What I'm going to do is I'm going to make a Gaussian pillbox. This surface is parallel to the conductor. I go in the conductor. And this now is my Gaussian surface. Let this area be capital A. And let's assume that it is positive charge so that the electric field lines come out of the surface like so, perpendicular to the surface. Always perpendicular to equipotential. So now if I apply Gauss's law, which tells me that the surface integral of the electric flux throughout this whole surface, well, there's only flux coming out of this surface here. I can bring that surface as close to the surface as I want to. I can almost make it touch the conductor. So everything comes out only through this surface.
So, in a sense, this is doing what I'm talking about. So the way you want to figure out how close or far away your charges can be on the surface is to just take the flat surface and compare it to the mean, the average of your curved surface, and you get some kind of angle, thetas or something, and that'll tell you how close your charges can be, pretty much. So that's another way of interpreting Gauss's law, is by understanding it's how I mean, obviously curves can go both ways, so and that's why the interior curves are even harder for the charged bits to deal with. You could have less density, but that's all. It's just a way of describing the fact that you can almost think about it, a curve up as the charges kind of piling on each other and just saying, no, we can't do that, so they have to spread. Yeah, so if you just compare them to a flat plane where they have, well, it's really not the maximum, because I guess, like I said, the interior curve has a higher maximum. But anyway, that would be a normal, and then just compare things to that normal, and you can find out how much pressure there would be. Yeah.
And so what comes out is the surface area A times the electric field E. The A and E are in the same direction, because remember, E is perpendicular to the surface of the equipotentials. And so this is all there is for the surface integral, and that is all the charge inside. Well, the charge inside is, of course, the surface charge density times the area A divided by epsilon zero. This is Gauss' law. And so you find immediately that the electric field is sigma divided by epsilon zero. So whenever you have a conductor, if you know the local surface charge density, you always know the...
All right, so what he just did there was he just converted the round surface into a flat plane and recognized that there's less area, so he converted the area of the roundness into the area of the flat thing. So the flat thing now is a representation of the curved part. So obviously the more curved it's going to be, the more surface you're going to be compensated for in that one little Gaussian surface. So you're basically you're basically making the thing straight, and then measuring how much, if you bent the curve with the charges where they are now on the round, and then you'd have like a cone, which would be your little top thing is representing how much surface area on the curve. So the more the curve, the more charge that would be represented by this much straight. So if it was straight, how much charge density have you lost?
Local electric field. And since the surface charge density is going to be the highest here, even though the whole thing is an equipotential, the electric field will also be higher here than it will be there. I can demonstrate this to you in a very simple way. I have here a cooking pan, and the cooking pan, I used to boil lobsters in there. It's a large pan.
Yeah, I wish you wouldn't do his little. I would used to, twist the neck of geese, and I, boil little innocent creatures. You could save me your lifestyle stuff.
The cooking pan I'm going to charge up, and the cooking pan here has a radius, whatever it is, maybe 20 centimeters. But look here at the handle, how very small this radius is. So I'm going to put charge on there, and I'm going to convince you that I can scoop off more charge here where the radius is small than I can scoop off here. I have here a small flat spoon, and I'm going to put the spoon here on the surface here and on the surface there, and we're going to see from where we can scoop off the most charge. Still charge from the previous lecture. So here we see the electroscope that we have seen before. I'm going to charge this cooking pan with my favorite technique, which is the electrophorus. So we have the cat fur and we have the glass plate. I'm going to rub this first with the cat fur, put it on, put my finger on, get a little shock, charge up the pan, put my finger on, get another shock, charge up the pan, and another one, charge up the pan, make sure that I get enough charge on there, rub the glass again, put it on top, put my finger on, charge, once more.
All right, so the idea is you don't put your finger, you put your finger on briefly, just to cause the current to flow, which takes whatever density of charge there was and moves it from the insulator to the conductor, but it's the opposite charge to what's on the glass. So that's the part that's still kind of weird. It's obviously providing, he's providing, that's, oh, see, I'm so stupid. All right, there's a bunch of positive charges on the glass, and so when he puts the plate on it, not much is happening because it's an insulator, so some of the charges might drift into the pan, but not too many. But it's close. It's really close to the surface. So the positive is making the surface go negative on the pan, the pot, the lid, whatever. So it's wanting to go negative. It's wanting to really bad. But it just has the ions that are inside, it just has the electrons inside the lid, so it can't go very negative. It wants to go a lot more negative. It doesn't have enough negatives to equal the positives on the glass. So when he touches it, he's supplying the negatives. The ground has an infinite number of both positives and negatives, so not an infinite number, a big pile, Earth-size pile of them, and an endless supply, seemingly. So when he touches it, he's supplying the metal thing with the opposite charge it wants to fully charge to equal the charge that's on the glass, the positive charge. So he's not pulling the charge off the glass. The lid is going opposite, and then he's providing the extra electrons, or he's taking away the electrons, either way, ions wise. He's adding the ionization appropriate to that charge by touching it. He's providing a stream for the opposite charge. Alright, so we got that nailed.
And once more. Let's assume we have enough charge on there now. Here is my little spoon. I touch here the outside here of the can, of the pan, and go to the electroscope, and you see a little charge. It's very clear. What I want to show you now, it's very qualitative, is that when I touch here the handle,
and by his math, he's saying this number should be gigantic, but this circumference is huge compared to this one. So we're a lot more than 5 times or 10 times. So, but he's not going to give us that kind of qualitative answer. But it would be curious to know exactly what the charges are here, because this should be a substantial difference in charge, like 10,000 volts versus 500 volts or something.
It's a very small radius that I can take off more charge. There we go. Substantially more. That's all I wanted to show you. So you've seen now in front of your own eyes for the first time that even though this is a conductor, that means that it is an equipotential, that the surface charge density right here is higher than the surface charge density here.
All right, the surface charge density, I guess that isn't exactly the same as voltage, but it's something similar. All right, so we still got a question there. Yeah. I mean, it's breakdown voltage in a sense, blah, blah, blah. You go through all this stuff. Yeah, I mean, it's got to be a higher voltage. It's got to be. Or it wouldn't be able to drain off quicker or more likely to drain off.
Only if it is a sphere, of course, for spherical symmetry reasons, will the charge be uniformly distributed. If the electric field becomes too high, we get what we call electric breakdown. We get a discharge into the air, and the reason for that is actually quite simple. If I have an electron here, and this is an electric field, the electron will start to accelerate in this direction. The electron will collide with nitrogen and oxygen molecules in the air.
All right, so that's how they say it happens. All right, so they say the electrons fly and do all this communicating of the pressure. I would argue that it's the atoms are what's holding the pressure, not the electrons. So they can go from atom to atom, yes, but they don't like fly somewhere long. They just fly between the atoms. So it goes from being an atom of an ion of, say, an oxygen atom turns into an ion of a nitrogen atom over here. The electron is migrating in a direction, but it's migrating in that direction through the atoms by bouncing into them, or for them bouncing right into each other. So again, there's two ways to communicate the pressure. Have the electron shoot off at a pressure and hit some other atom with that extra pressure and impose more pressure by becoming part of that atom, ionizing it, adding an electron to it. Or the atoms can just bang into each other, which means their electrons are going to bump into each other. And they're not going to hit, obviously. They're just going to bounce off each other's force. So the one that has more pressure is going to push into the one that has less pressure, and the pressures are going to become more equal, or there's going to have to be an exchange of the ion, the electron.
And if the electron has enough kinetic energy to ionize that molecule, then one electron will become two electrons, the original electron plus the electron from the ion.
So you can ion both ways. You either ion into a positive ion or a negative ion, which means the electron stays in the atom, or the electron knocks another one out and makes another atom that's short an ion. So the cascade thing can only happen in one direction. That is, from making things that have an excess of electrons to something that has less electrons.
And if these now start to accelerate in this electric field, and if they collide with the molecules, and if they make an ion, then each one will become two electrons, and so you get an avalanche. And this avalanche is an electric breakdown.
Yeah, so I don't think this is correct at all, because the energy of the electron is used to make ions. You can't make an ion for free. So you can't just make another free electron and have the same energy you had as before. You have to lose energy somewhere. So you can't have any perfect chain reaction. You're supplying more pressure. It's not, it's not a chain reaction where you're like a nuclear one, where I throw one neutron into the pile of crap and the one neutron does everything. Just one neutron blows the whole thing up, technically. You're not doing that with electricity. Electricity, you keep pumping electrons. You're pumping new force. You're not making a cascade of old force. More force goes in. As you make a path, more and more electron pressure goes through and is making the cascade. So it's like putting a little hole in a dam, and the dam starts to crumble, and then you get more and more pressure. So I would use that analogy, not this cascading analogy. I don't think there's any chain reaction. The chain reaction is obvious. The reservoir is full of water, and the pressure is going to get through eventually.
And you get a spark. When the ions that are formed become neutral again, they produce light. And that's what you see. That's the light that you see in the spark.
Again, yes, and that's energy, so that's more draining. So the pressure is coming through the little hole in the dike, you could say, and some of the water squirts this way, and that's what you're looking to pressurize. Is this a new area over here, this wall you want to push? But some of the water is coming out sideways, which is sort of waste, and that's sort of like the light. The light is energy you're losing from the process of pushing. So the pushing isn't pure enough. So the light is just evidence of waste, of heat, of whatever you want to call that. It's not really directed at the purpose, which is to move the current down the conductor. It's something else.
So sparks will occur typically at sharp points, at areas where the curvature is strong, whereby the radius is very small. That's why the electric fields are the highest. How strong should the electric field be? Well, we can make a back-on-the-envelope calculation. If you take air of 1 atmosphere, dry air, at room temperature, then the electron on average will have to travel about 1 micron, which is 10 to the minus 6 meters, between the collisions with the molecules. It's just a given. On average, sometimes at a...
So he's just talking about what the average distance is between the molecules at any one point. But the real point is they don't have to, the electron doesn't have to travel that distance, because obviously the molecules will interact with each other in the sense that their electrons will interact with each other directly, and whatever, if one is ionized, it's going to convey that ionizing pressure to the other atom.
So more, sometimes a little less, because a random process, of course. To ionize nitrogen, to ionize oxygen takes energy. To ionize an oxygen molecule takes 12.5 electron volts, and to ionize nitrogen takes about 15 electron volts. What is an electron volt?
So again, these are just averages too. So in a sense, it all kind of depends on how you hit, right? So how you hit the atom, whether you ionize it or not, it kind of depends on whether you hit it perfectly, like right in between 2 electrons, or whether you actually bump into the other guy's electron in some way. So I think those numbers, again, are just averages. They don't have anything to do with the fact that it can happen easy or it can happen hard.
Well, an electron volt is a teeny weeny little amount of energy. It's 1.6 times 10 to the minus 19 joules. Electron volt is actually a very nice unit of energy. Because once you have an electron at rest, and it moves over a potential difference of 1 volt.
At rest. So again, it's not going to move over any potential difference if it's at rest. So again, that, it's just not the right way to, in my opinion, to point out that it has to be under pressure. So it's locked in an atom, but it's under pressure, and then it's going to have to get ejected to pop into the other atom, and it's going to have enough pressure where when the other atom hits it, there's enough. This atom has less pressure, and it's going to slide into the other atom. But that requires some energy. Every time they bang into each other, they're going to do this energy exchange. But the bottom line is you're taking the electron, which has an average capacity to have a pressure of 1.6 times 10 to the 19 pressure. That's what the pressure on the electron. If the electron is in a free environment, it doesn't have any energy. Zero. Its energy is completely dependent on what's pushing it. If it doesn't have anything pushing it, it's like a water molecule in the reservoir, that's on the surface. It's just sitting there, Doesn't have anything happening really. Nothing's pushing on it. Well, it's sort of gravity is in this sense. So I was trying, obviously the deep water molecules are under a lot of pressure, so I'm just trying to think of some way to analogize it. But it's like it doesn't mean anything unless there is somebody pushing on it.
It gains in kinetic energy. That's the definition of an electron volt. It gains 1 electron volt. It's the charge of the electron, which is 1.6 times 10 to the minus 19 coulomb, multiplied by 1 volt. And that gives you then the energy, 1 electron volt. And so...
All right, I would argue a slight piece of evidence on my side is whenever this, you ever have this breakdown voltage or you have these sparks and the rest of it, they tend to be blue, which means their energy is high. The pressure was high that created that photon. So that bit of that event, whatever it was, obviously had a lot of energy, the pressure, because the photon it created is a high frequency. It's close together. So the electron that created that was close to another electron. So when an electron event creates blue light, it's because the electron was under high pressure, higher pressure.
What it means then, let's assume that this number is 10 electron volts. We only want a back on the envelope calculation. So we want the electron to move over a potential difference delta V, which is roughly 10 volts, and we want it to do that over a distance delta X, which is 10 to the minus 6 meters. That's your 1 micron. And if that happens, you'll get this enough kinetic energy in the electron to cause an ion. So what electric field is required for that? That is delta V, the potential difference, divided by the delta X. So that is 10 divided by 10 to the minus 6. So that's about 10 to the 7 volts per meter. That's a very strong electric field. In reality, when we measure the electric fields near breakdown, it is more like...
So 10 to the 7th, he's leaving us to figure that out. So that's 1,000,000 volts or 100,000 volts? 7 zeros. I can't do it in my head. He's expecting a lot. 5 would be 10,000. So, right? No, 10,000 before. So 7 has to be 1,000,000. Yeah.
3 million volts per meter, but it's still very close. It was only a back on the envelope calculation. So very roughly at...
So he's got 1,000,000 volts is close to 3 million volts. Okay, fine. It's okay with me.
1 atmosphere air, room temperature, when the air...
Well, I forgot about the 10. Yes, well, never mind. So obviously no 3 in there anywhere.
is dry, we get electric breakdown at about 3 million volts per meter. When the ions neutralize, you see light. That's why sparks can be seen. They heat the air. They produce a little pressure wave. So you can also hear noise.
So the point would be is that if you could dry the atmosphere, take the water out of it, you make it a lot less conductive. Less molecules also. So that would make it less conductive. So you can increase the amount of voltage before it goes to ground through the atmosphere. So the breakdown voltage is just specific to our atmosphere. It's not, it changes wherever atmosphere you go into, and so space theoretically would have a breakdown voltage of a zillion volts or whatever.
If you had two parallel plates and you would bring those plates closely together and suppose they had a potential difference of 300 volts, then you would reach an electric field of 3 million volts per meter when the distance d is about 1/10 of a millimeter. So that's when you expect spontaneous discharge between these two plates. In practice, however, it probably will happen
1/10 of a millimeter? That sounds really small, actually, for 300 volts. I think you could get 300 volts to jump a little further than that. 1/10 of a millimeter? I think there's something wrong with that number. 300 volts is a little jumpier than that, I think.
when the plates are further apart than 1/10 of a millimeter. And the reason for that is that there's no such thing as perfect plates.
Okay, so yes, so in my experience, obviously the surfaces would be pretty crappy, so they'd have those little hills on them, so it would break down much sooner than 300 volts. So at 300 volts you could have them further apart and still get a spark because of those hills.
The plates have imperfections. That means there are always areas on the plate which are not flat, but are a little bit like what you see there. Small radius, and that's of course where the electric field then will be larger, and that
the voltage will be larger, so the breakdown voltage at that point will be much lower because it's a higher voltage. So you'll get a spark from like the 10,000 volts at the little peaks rather than the 1,000 volts, let's say, across the plates, that kind of thing.
Where the discharge will occur first. However, if you touch the door knob and you get a spark, you feel a spark, and you look at the spark and you see that when you're 3 millimeters away from the doorknob that the spark develops, you can pretty sure that the potential difference between you and the door was of the order of 10,000 volts, several thousand volts at least, because over 3 millimeters it requires 10,000 volts to get to 3 million volts per meter. When you comb your hair, or when you take your shirt off, you get little sparks, you can hear them, and if it's dark you can see them, and you can be sure that at the sharp ends of this hair, of the fabric.
Well, I'm just saying this calculation doesn't do you much good because it's wrong, so they ought to just factor in the fact that surfaces you ought to have common surfaces versus perfect surfaces, because even his Venn diagram is a huge difference. I mean, he gets breakdown voltage at 300,000 and his Venn diagram should be good for 3 million. So, I mean, that's a substantial degrade from the mathematical prediction. I mean, the mathematical prediction is he should be able to get 3 million volts on that thing in a perfect world, and he can only get 300,000.
That you have developed electric fields of the order of 3 million volts per meter, and then you get the automatic breakdown. Now, of course, high voltage alone doesn't necessarily kill you. What matters is not so much the voltage to get killed, but it's the current that goes through you. And current is charge per unit time.
Yeah, well, I don't buy that either. I mean, obviously you can have an awful lot of low voltage go through you, and it's not going to, who cares? Yeah, I mean, you could ground yourself with your car battery and, run the car through you, and you're not going to feel nothing.
And so in SI units, it would be coulombs per second, for which we write a capital A, which stands for ampere. The man who did a tremendous amount of research in this area, Frenchman. And so if you touch the doorknob, the instantaneous current may actually be quite high, maybe an ampere even, but it may only last for 1 millisecond. And so that's not going to kill you. We all know that when you comb your hair, that you don't die. And we also know that when you take your shirt off, even though you may hear the sparks, that's not lethal. So maybe in a future lecture we can discuss in some more details what it does take to actually execute someone electrically, which is very unpleasant, but nevertheless, we would have to evaluate how long the current should last, how strong the current should be, and then also...
Yes. Well, that's all quite disgusting. But yeah, that seems to have something more to do with trying to get the heart to start fibrillating, and you have to kind of wait, because the person don't die until the fibrillation lasts long enough for the brain to get killed. So yeah, so you have to keep it in a state of fibrillating. So, that wasn't a good idea, Gary. Anyway, monitor's just gonna. I'm just going to have to kill it. I had it where it was. Well, it does this. It works fine for a while, and then it does this bad period thing.
So, during which parts of the body the current would cause lethal reactions. So I want to be a little bit more quantitative now, and deepen our knowledge of the Venn diagram. Slowly we're going to understand how the Venn diagram works, and today I want to calculate with you how much charge we can put on the Venn diagram and what the maximum potential is at the surface. If we charge up the Venn diagram with charge Q, then the potential of the surface is an equipotential is Q divided by 4 pi epsilon 0 r.
So it's a third of a meter, which I don't know off the top of my head. What is that? Foot.
And the electric field right here at the surface would be Q divided by 4 pi epsilon 0 r squared. So in this case of spherical symmetry, we have that the potential V equals E times R. But we know that E cannot exceed 3 million volts per meter. And so that gives you now a limit on the potential that we can give the Venn diagram. So if you substitute in here 3 million volts per meter, you can calculate what potential you can maximally reach for a given sphere with a given radius.
Yeah, I'm trying to think of the meter is on the surface, or there's the meter, the R number. Well, we'll find out.
And if we here have the radius and we here have the voltage, then if the radius of the sphere were 3 millimeters, then you could not exceed a voltage of 10 kilovolts. If you did, you would get this automatic electric breakdown. You would get a spark. If you have a sphere of 3 centimeters, that would be 100 kilovolts. And our Venn diagram...
Yeah, well, why don't you give us the Venn diagram numbers or something close, like a foot. So the Venn diagram is about 2 feet across. A little more.
Which has a radius of 30 centimeters.
So that's less than. So it has a diameter of 60 centimeters, which is 60% of a meter, something like that.
Therefore be 1 million volts. You could not.
Okay, so 1 million is the number. So sorry, my mistake. So its natural capacity is supposed to be 1 million, and he can only charge it up to 300,000. So you have a 1/3 degrade because of the atmosphere. So all these calculations are nice, but they ought to just know that, well, you got to divide them by 1/3 because that's what you're practically going to get in Earth atmosphere.
Exceed that. And in practice, in fact, this one doesn't even make it to 1 million volts. The sphere is not perfect. There are imperfections of the sphere. There are areas which have, so to speak, sharp points. And so we won't make it to 1 million volts. We get a breakdown maybe at a few 100,000, maybe 300,000 volts. You can now also calculate what the maximum charge is on the Van de Graaff, because if the maximum potential is 300,000 volts, you know the radius is 0.3 meters, so you can calculate now what the maximum charge is that you can put on the Van de Graaff using that equation will give you 10 microcoulomb. And so the maximum potential for our Van de Graaff is of the order of 300,000 volts. So this gives you now a feeling, a quantitative feeling for numbers, for what the... Can I put this down? So this gives you an idea of what our Van de Graaff can do. And later we will understand how the charge gets there. But at least you have some feeling now for potentials and for the charges that are involved. Here's my Van de Graaff. And I approach the Van de Graaff with a sphere which is connected to the Earth. And if this Van de Graaff has positive charge on it, then this sphere will become negatively charged through induction. And so you get field lines which go from the Van de Graaff to this object, always perpendicular to the equipotentials. So they go like this. And so the electric field here will probably be the strongest. And so
they draw these lines as perpendicular lines because that's the average, really. So theoretically, you have to think of the charge as a little sphere on top of the sphere, like a little lump. And you could theoretically say it could radiate in all these directions. But these all cancel out, and these all cancel out, and this is the main direction. If you average that charge out, this is the direction of the average, because the charge will be evenly distributed. Just, it's the same truth for how a photon's created off a surface. It can leave at any direction, but when you average all the directions, this is the direction. And when they're all doing the same thing, it just ends up being that they're mostly doing this. If you add up all of these angles over a distance, it would just look like straight lines.
Spark will then develop between this sphere and the Van de Graaff, provided that you are close enough, so that you do achieve a electric field close to this sphere of about 3 million volts per meter. And I will show you that later. You will see more sparks today than you've ever seen before in your life, but I want you to appreciate a little bit more about the sparks before I demonstrate that, so you get a little bit more out of it. If I approach the Van de Graaff not with the sphere, but I would walk to the Van de Graaff being very courageous like this, I'm also a pretty good conductor, I'm also connected with the Earth, then the chances are that the spark would develop first between my nose and the Van de Graaff, because that is the smallest the sharpest curvature, the smallest radius, or certainly my head.
Alright, so because he's grounded, what's going to happen is because positive is attracted to negative, the bunch of the negative ions are going to kind of move to the surface. So let's say the Van de Graaff is positive, and so he's going to have a bunch of negative ions move to his surface. And he's going to run out of them. He's not going to have enough. So he's going to pull some more from the ground. So he's just got an endless supply of them from the ground. So he can create a very high voltage on himself because he has an endless supply of them. He can just keep pumping them out of ground. So he can match whatever voltage he's encountering with the opposite voltage.
Would be a good candidate for being hit first. If I approach the Van de Graaff like this with my hand stretched, then chances are, of course, that the sparks will first develop between my fingertips, because it's a very small radius and they're very close to the Van de Graaff, and so that's where the discharge will.
See, the more the more charge bits you collect, the more they're attracted. So that's what the density thing does. So the more dense, the more of them there are, that's like a bigger and bigger magnet. It just makes them attract more and more and more. It creates more force for attraction. So that's why that's just adding to your potential to create this spark, is because you just keep increasing the density.
Occur. So before we will enjoy some of this, you will enjoy it, I will enjoy it less. I want to talk a little bit about lightning with you first.
Which does get me thinking about the the whole atom argument, because the atom is basically although we count all the electrons as some kind of collective group of things, they really individually act with the protons. And what are they really individually acting with? It's one electron against a huge big ball of protons, a big nucleus. So the electron is very uneven in terms of its charge density, or whatever you want to call it. So it's something to consider, that they always write it as 1-to-1, but the relationship really isn't 1-to-1. That's why the electron is so far away from the nucleus.
There are 400,000 thunderstorms every day on average on Earth. 400,000 thunderstorms. There are about 100 lightning flashes every second. In general, the top of a thundercloud becomes positive and the bottom becomes negative. The physics of that is not so easy and probably incomplete. And I will not go into the details of the physics, but it does have to do with the flow of water drops. They become elongated, they can become charged because of friction, and they can break off, and they can transport charge. I will simply give you some facts. And so I will accept the fact that the cloud is going to be charged. This is the cloud. Positive at the top, negative at the bottom, and here is the Earth. Because of induction, the Earth, of course, will therefore become positively charged here. And so we're going to see field lines, electric field lines.
This, you would think, would be something easily detected, was when you're becoming positively charged. So I was thinking of building an antenna that's already positively charged, and then separate from ground, have an ungrounded antenna above the Earth that was already positively charged. And I could charge it to a higher voltage, and you would think that would become a more effective lightning rod because it's already pre-charged, and if you charge it to a high enough voltage, but then it can't get any higher, is the trick, right? So unless you connect it to ground, it can't get more positive ions, so it can't go any higher than what you pre-charge it to. That's the downfall. Okay. Never mind. Obviously, between the cloud and the Earth, you have to have a voltage differential that's absolutely insanely huge, theoretically. It's got to be a lot more than a Venn diagraph.
Which go from the Earth to the cloud, always perpendicular to the equipotentials. Something like this. I'll give you some dimensions. This may be something like 5 kilometers. This vertical distance, d, is about 1 kilometer. These are typical numbers, of course. It can vary enormously.
Yes. What's interesting, too, to think about is, let's say you're standing on the ground when this thing is happening, and you're getting charged, but you won't feel that. And you'll be covered, essentially, with ions of like 1 billion volts or something. You'll have that voltage on you somehow, relative to that cloud. So, I mean, in theory, I'm just thinking if you run a line from ground somewhere else, like you have a wire, like your phone line or something that's, going way far away before it gets grounded, could you just, zap that voltage off yourself? I don't know. It's curious. I have to do some thinking about this concept, because it just doesn't sound quite right.
From thunderstorm to thunderstorm, and this height is something typically like 10 kilometers.
If we oversimplify the situation by assuming that the cloud and the ground behave like plane parallel conductors, then we can roughly calculate the potential difference between the cloud and the ground.
All right, so I think that's sort of, so he's added that little bit about how, simplifying. And that's part of the problem here. This is too much of a simplification. Because I think what's happening with the voltage is it's migrating in steps to the trillion volts here in the middle of the atmosphere. So at these surfaces, the voltages aren't nearly as high as they're going to end up being here, where you're going to complete your bridge. So you're building a bridge essentially from both sides, and where the bridge starts is 10 volts, where the bridge ends is a trillion volts. I think that's why we don't notice this huge voltage difference.
I will do that first, but I warn you in advance that this is not kosher.
If we make the simplified...
All right, so he's saying it's not kosher, the simplification. So, okay, fine. So I guess this part is basically just a little bit of a, well, let's pretend or something. Well, it's okay. I mean, it's basically saying, look, this isn't quite right. This isn't the quite right answer. Okay, so let's listen to it anyway.
Assumption that the electric field is more or less constant here. It's like having two parallel plates where the electric field is constant between them. Then the potential difference, delta V, between the bottom of the cloud and the Earth is simply the electric field times the distance d. So this becomes E times d. But if the breakdown occurs at 3 million volts per meter, so we get 3 times 10 to the 6, that is for E, and the distance between the cloud and the Earth, let's take 1 kilometers, so that's 10 to the third meters. So we get of the order of 3 billion volts between the Earth and the clouds.
But now comes the catch. As I was told by Amir Risk of lightning electrotechnologists, that you cannot extrapolate the values from a small uniform field gap between two plates to a lightning strike. This is because the conditions for the continued propagation of an electric discharge are not the same as the conditions for its initiation.
Okay, so sort of saying something like what I'm saying is that as the conductor is being built, there's no billion volts. And the billion volts shows up once you've built your conductor, essentially. So it's not, the process is more incremental through the atmosphere. You didn't say exactly that, but it's something like that. The initial conditions are not the same as the zapping conditions. By the time the zap shows up, the conditions are very different than the conditions were when the lightning was starting to go through its procedure.
If an electric discharge is spanning a gap that is longer than a few meters, a discharge can move in electric fields that are orders of magnitude smaller than the electric fields that initiated the original electron avalanche.
All right, so again he's using electron avalanche, but whatever, it's not an avalanche, but whatever. You're feeding it. It's not a chain reaction. It's a fed reaction. Like I said, a nuclear bomb it's already pressurized. I just throw a neutron in, the whole thing blows up. Electricity would be pumping the explosion. I have to pump the explosion.
At a height of 1 kilometer, that is somewhat lower than 3 million volts per meter. Consequently, the potential difference between the cloud and the Earth can vary between 50 million and 100 million volts. It can even be either positive or negative.
The details of the physics of the discharge, very complicated. But I want to...
Which is also just seems a little bizarre that it can switch. You can have different polarities on the cloud. I would imagine they're always kind of charged the same way, but they say not. So sometimes you're pulling positive ions, sometimes you're pulling negative from the Earth. Apparently. So, anyway, well, a little bit more.
Share with you some facts without giving detailed explanations. The start of the lightning begins when electrons begin to flow from the cloud to the Earth. They form a funnel which is about 1 to 10 meters in diameter, and we call that the step leader. The step leader moves about 100 miles per second, and so it comes down in about 5 milliseconds. 5 milliseconds from here to here, and it takes about half a Coulomb to the Earth. Half a Coulomb for about 5 milliseconds, that means the current is about 100 amperes.
I think it's kind of obvious that there's not just some straight line things 10 meters wide that comes down to the Earth. Obviously, it goes through the atmosphere's density. That's why the lightning is crookedy. It's because there's layers of atmosphere that are more conductive than other layers of atmosphere. So, this is a bit simplified.
The step leader creates a channel of ionized air, full of ions and full of electrons, which is an extremely good conductor. And when this step leader reaches the ground, there is this highly conductive channel, and the electrons can now very quickly flow from this channel to the ground. And that's...
It's not really highly conductive, it's just that it's dense enough. So it's still probably not very good conductor, but it's enough of one to push the frickin' pressure through. There's enough atoms to do the job.
Starts first right here at the surface of the Earth. That's where the electrons will first go to the Earth, and then successively electrons which are higher up in the channel will make it down to the Earth. And so you're going to see electrons going through the channel to the Earth, but first the electrons are closer to the Earth, then the electrons farther away, and then even farther away. And this is actually where most of the action occurs. The current is now enormously high, 10,000 to some 100,000 amperes, and you heat the air, you get a tremendous amount of light, the ions recombine, and you get pressure, heat produces pressure, and there comes your thunder. And so most of the action is not in the step leader, but is in the second phenomenon, which we call the return stroke, which is from the Earth to the cloud.
You basically burn the hell out of the atoms, so that's what the light and the pressure is the atoms are getting their electrons fried off.
And the speed of that return stroke is about 10 to 20% of the speed of light. During the return stroke...
So again, the slowness is an indication that this isn't just force moving. It does have to move through. It has to push electrons. And obviously the speed of electrons would be way too slow. So if electrons were doing the communicating over great distances, they're not going to move anywhere near the speed of the force pushing them. So you got to know that these electrons are close to each other, that the atoms are playing a key role in allowing the electrons only to have to move a tiny distance, where most of the pressure will be through electrons that are already in pressure. That is, the atoms are already pressurized, so when you push one, you push this end. That's the quick movement. You have to make a stick out of the electrons, a stick of electrons, and the stick can only be created by the atoms. So the atoms are essential to having a cascade of the electron, where you push one at one end, like the metal balls. You have to hit one at one end, the other one pops out at the other end. That's much quicker than having each ball have to do the movement.
It's about 5 Coulomb exchange between the cloud and the Earth, and 5 Coulomb is a sizable fraction of the total charge that was on the cloud to start with. After a return stroke, maybe 20 milliseconds later, this whole process can start again. You can get a step leader, and you can get the return stroke. However, the step leader will now follow exactly the same path that was made before, because that's where the air is ionized, so that's where the conductivity is very high.
That's where the atoms are, frankly. Whether they're ions or not, that's where there's atoms.
Easiest way to go. And this process can recur 5, 10, maybe 15 times. So what appears to you as one lightning bolt, in fact, could be 10 flashes back and forth between the cloud and...
See, the ionization creates charge differentials in the atmosphere. So when you start ionizing, you start attracting other atoms. So the density of that area becomes more dense with atoms, because you've created a little bit of a magnetic or charge scenario, and that migrates anything that's a negative ion, and you have positive ones, they're going to move towards the negative ions. You make positive ions, you're going to move all the ones that are negatively ionized. So you're automatically creating a magnet, and there's some iron, there's some paramagnetic material around, and it's moving towards the magnet you're creating, sort of. So you're making the atmosphere denser by ionizing it. You ionize a little bit of atmosphere, you'll automatically create more atoms there because you'll attract the opposite ions.
The Earth. And the real light is not in the step leader, that's very little light, but the real light is in the return strokes. So 10 return strokes, which may be 20, 30, 40 milliseconds apart, appear to you and to me only as one flash, which would take place maybe in as little as a tenth of a second. And during these 5 or 10 return strokes, you exchange between the cloud and the Earth maybe a total of 25 to 50 Coulomb, and that of course will lower the potential difference.
Okay. Yes, the cloud loses its charge and has to build it up again eventually. So anyway, I think that's probably enough for now, and so we'll be back and finish this up. But interesting subject. We once again have learned something. Some of it we learned, and some of it we oh yeah, so that must be this, this, and this. Yes. So constructive, I think. So till the next time.